Thank you to Squarespace for supporting and sponsoring this video.
We keep a radiation monitor close.
Oh, hi everyone. I think this is how you imagine the consequences of some radioactive leak to look like. Or this is what you imagine when you hear something about radiation. But what action should actually be taken when some nuclear accident happens, and how to evaluate the degree of safety when coming into contact with radioactive chemicals? Well, let's find out. It has become a recent trend for many people to get anxious tools when they hear something about radiation and they immediately recall the Chernobyl nuclear disaster. But this hasn't always been the case. For instance, 100 years ago, people gladly rubbed radioactive chemicals into their skin and took radioactive pills in order to prolong their lives and obtain some supernatural powers. I think in order to realize what radiation actually is and how dangerous it can be, first we need to turn to the history of this term. The term was first coined in the 20th century after Becquerel experiments with uranium ore, when for some reason light-sensitive plates in a closed box started glowing along with the bits of uranium ore placed nearby. After Becquerel's discovery, it was the Curie's family that managed to measure the quantity of radioactive rays for the first time using the device invented by Pierre Curie, which was the first invented radiometer in the world, or simply put, a radiation detector. Thanks to this device, Marie Curie managed to discover a new chemical element in uranium ore, which was unknown earlier. It was radium, which emitted thousands of times more radiation than regular uranium ore, which is why she was awarded the Nobel Prize in Chemistry in 1911. It is worthy of note that at that time, no one knew that powerful radiation can harm people and even burn skin, which is why, being unaware in this fact, people decided to start earning money from the newly discovered radium and also other radioactive chemicals. From the 1920s until the 1950s, hand creams with radium, toothpastes with thorium, uranium dishes and lots of other dodgy items were on sale. These items began to be banned only after countless complaints and tragic accidents which happened after using such radioactive things. But in reality, small quantities of radiation surround us almost everywhere we go, because all objects around us buzz, indicating a slight level of radioactivity. But actually, what are these radioactive rays and how can they be measured quantitatively? To find out, I went to the State Service of Radiation Control, where I can investigate this matter more thoroughly. I think you may still remember from school that radioactivity or ionizing radiation can be divided into three basic types, namely alpha, beta and gamma radiation. For instance, there exists such a metal as americium, which practically doesn't occur naturally. Substantial amounts of it can only be obtained in nuclear reactors, that is why it costs 30 times more than gold. However, in contrast to its precious fellow metal, americium atomic core is 2.5 times bigger than that of gold, which is why it's more unstable. In other words, americium has such a big core that it collapses under its own weight, which is why it always breaks into smaller bits, which are helium atomic cores, 2 protons and 2 neutrons, which form a stream of alpha particles. Of course, it cannot be observed visually, and when we look at the americium-controlled radioactive source, we cannot see any particles. Of course, because their size is thousands of trillions times smaller than a human hair, we need a special device with a highly sensitive detector made of organic crystal of plastic material, coated in zinc sulfide. When alpha particles get on the device detector, an electric signal is registered, which is converted by the electronic circuit into readings on the display. As you can see, about 20 alpha particles per second come out of this source, which are shown as the amount of decays per second. But is it dangerous? In reality, if you don't swallow such a controlled source or don't wear it attached to your skin, everything should be alright. The thing is, alpha particles are quite big and move at a rather slow speed, which is about 5% the speed of light, which is why they can quickly collide with air molecules, or other molecules and waste all their energy. Because of this, the entire stream of alpha particles can be blocked by a sheet of paper. This can easily be confirmed by one experiment. We put a sheet of paper on the americium source, and after that, the device stopped showing any readings. In reality, though, things are not simple. For instance, if we grind a piece of americium with a piece of sandpaper, a lot of radioactive dust will be released into the air, which along with inhaled air would get into your lungs. There is no protective layer of hardened skin, which could block the stream of alpha particles, which is why it can damage a lot of unprotected cells, having destroyed their DNA and having led to fatal change in the lungs. That happens because of the large size of alpha particles, which can collide with any other atoms and steal their electrons. This process can be well observed when alpha particles travel through a layer of ethanol vapor in Wilson cloud chamber, leaving behind a thick trail of condensed alcohol vapor. But it's not that long. This means that if, for instance, an alpha particle collides with a nitrogen atom in human DNA, it will destroy a huge part of the genetic code in the human cell, which can soon lead to its death because of a large number of defects. This is the reason why it's dangerous to inhale such radioactive dust. But how can this dust be detected? For this purpose, there exist several special stations in different countries that daily filter the air through such glass fiber filters. Every day, used filters are delivered at the laboratory and loaded into a special plastic cylinder in order to fit to the dimensions of the measured object. After that, such a capsule with a filter is placed into a gamma-ray spectrometer, which detects whether or not there are any radioactive particles in the filter, and usually it takes 24 hours to make that measurement. After that, you can see an energy graph on the monitor, which appears as a result of the chain decay of the radioactive element. This graph can easily indicate whether or not the level of radioactive particles in the air is too high. For instance, in 2011, such a filter was used to detect the slight increase in the background radiation after the nuclear accident at the Fukushima nuclear plant, because of the radioactive dust that flow from the other end of the Earth. But in reality, the increase in the radiation was too slight that it was detected only thanks to highly sensitive equipment. That is why it didn't harm people. Besides, there is also a radiation detector on the roof of a radiation monitoring center, which constantly monitors the background radiation. That is why if there is an increase in radiation, it will immediately detect it. Besides alpha particles, there also exist beta particles, that is, fast-flying electrons, which form as a result of a radioactive decay of some radioactive elements. For instance, let's consider a controlled source with such a metal as strontium. To be more precise, its unstable isotope, strontium-19, which also forms as a result of radioactive decay of uranium in nuclear reactors. The configuration of protons and neutrons in the core of this isotope is such that one neutron constantly wants to turn into a proton, releasing a fast-flowing electron or beta particle, and also forms an antineutrino, and after that it turns into an unstable yttrium-90, which radiates a beta particle again, and finally becomes a stable zirconium. As a result, this controlled source with strontium-90 can release trillions of fast-flowing electrons, which, just as alpha particles, can't be seen, but they can easily be detected with the help of a dosimeter equipped with a Geiger-Müller detector, that is, with a single gas discharge tube. Just as was the case with alpha particles, the detector indicates only the number of decays per minute, that is how many beta particles hit the device detector and cause the change of electric signal. Beta and alpha radiation is not measured in sieverts or Röntgens. Besides, beta particles can also be observed in Wilson cloud chamber, that is, in a chamber oversaturated with ethanol vapor, which is alcohol. When the button is pushed, a strontium source gets into the chamber filled with oversaturated ethanol vapor, which is why there immediately forms hundreds of fast-flowing electron tracks, which leave their marks made of condensed alcohol. The difference in penetrating power of beta particles becomes obvious, because, for instance, alpha tracks of alpha source with americium are much shorter, because alpha particle has a small penetrating power. In contrast to alpha particles, beta particles, because of their smaller size, can penetrate much deeper into the human body, but because of their small mass and energy, they don't do a lot of harm. Of course, unless you stand too close to it or even lick it. What matters is to protect your eyes, because a powerful stream of beta particles can damage your cornea. But still, when coming into contact with heavy atoms, beta particles can create so-called break-in radiation. For instance, if we shield the detector with a plastic beta filter and bring it close to the source with strontium-90, all the reading should be zero, because all the beta particles are blocked by such a thin layer of plastic. However, we can still see some readings concerning the beta particles on the screen. Most probably, this happened because the fast-flowing electrons coming out of the strontium collide with the metal atoms, having created so-called breaking X-ray radiation, which was detected by this device as beta particles or even gamma quanta. But what is that? What are these mysterious gamma quanta? If we take a look at the entire electromagnetic spectrum, we will see that gamma radiation is at the very end of this diagram, which means that this radiation has the shortest wavelength and therefore is the most powerful radiation in nature. In other words, this is pure energy in the form of waves, which can penetrate different materials rather deeply. During this process, gamma quanta form inside unstable cores of some elements, either after they release their alpha or beta particles, or after they got divided under the influence of neutrons. Such radiation is a leftover energy, forming as a result of transferring of an atom from an unstable state to a more stable state. From a chemical point of view, we can draw a good parallel if we ignite such a chemical as ammonium dichromate. This unstable chemical will start breaking down into more stable chemicals, such as chromium oxide, water and nitrogen. Also, energy will be released in this process, but not in the form of gamma rays, rather in the form of heat. In contrast to regular thermal energy, we can't feel gamma quanta, and we don't understand how far they can spread and how to hide from them. For instance, in order to completely stop the flow of gamma radiation from this controlled source with cesium-137 isotope, not even 2 cm thick layer of lead is enough from which this case is made. That is why the penetrating power of gamma radiation is the most dangerous, and it takes highly dense materials to stop it. For instance, when I was shooting synthesis of technetium in a hospital, a syringe with a radioactive chemical was placed in a tungsten case, which is one of the densest metal on Earth, in order to protect personnel from the powerful gamma rays. Also, thick glass containing lead protects well from gamma radiation, because the denser a material is, the better it protects from gamma radiation. The only advantage of gamma radiation is that it's electromagnetic, which means it has some spectrum, which is why it can be used for scientific purposes and in applied research. That is why, with the help of a special gamma spectrometer, it's possible to determine the exact content of all radioactive chemicals in the studied sample, which releases gamma rays. For instance, in order to determine the content of a radioactive source, we can use a rather expensive but precise dosimeter with a semiconductor detector from a highly pure germanium. In case you didn't know, germanium is a chemical element resembling a metal, but having unusual physical properties. When any gamma source is placed close to such a dosimeter, you'll immediately see a graph showing peaks in the released energy of this isotope. Also, this device allows to precisely identify the studied isotope in just a moment in order to be able to determine how to best use it. For instance, this is how radium-226 spectrum looks like, and here how that of cesium-137 looks. The germanium detector creates a little interference in the signal, which is why the obtained peaks are highly precise, which makes identification of the radiation source easier. This makes it easier for workers to decontaminate a contaminated territory and understand what protective measures are best to use. It's a pity through that such germanium detectors are not cheap at all. This one costs 130,000 euros. That is why oftentimes cheaper dosimeters with sodium iodide scintillation crystals are used to identify the source of contamination. Such one costs just 15,000 euros. Inside such a device, there is a special scintillation detector, which transforms the gamma quanta that hit it into an electric signal, Usually a scintillation crystal from sodium iodide activated with thallium is used there, like this one, but usually smaller ones are used. If you point an ultraviolet light torch at it, it will start glowing. Also it reacts to beam light with radiant radiation, converting it into visible light. For instance, if we place a controlled source with americium 241 close to the crystal and turn off the light, we can see a slight glow with the help of a camera with a long exposure. That's because after passing through the crystal, powerful gamma radiation converts into visible light. Of course, this happens only when there is a powerful stream of radiation. Loud doses of radiation almost don't create any glow. That is why a special photomultiplier is added to the scintillators of radiation detectors, which multiplies those microflashes of light and converts them into electric signals. Then, the software of this device can show you the level of radiation, and also, if the radiation is strong, it can identify what isotope radiates this powerful stream of gamma quanta. But still, for studying samples with low levels of radiation, for instance for determining the level of food or soil contamination, a more expensive and sensitive device for measuring radiation levels needs to be used. In another laboratory, a highly sensitive gamma spectrometer with a germanium detector for determining the spectrum of samples with low radiation levels is used. By the way, it has to be cooled in liquid nitrogen for getting readings that are as precise as possible. Such a device can cost over 100,000 euros. Any object can be placed in such a gamma spectrometer, for instance a jar with soil, and it can determine whether or not it's contaminated by different radionuclides and what isotopes it can contain. Thus, you can find out how certain radioactive isotopes got into the soil or foods, and then decide how to decontaminate them. The spectrometer itself is encased in lead and coated with copper and plastic. All these layers almost completely block the natural background radiation in order to make the spectrometer's reading as accurate as possible. The process of measuring itself is not fast and takes about a day, and after that you can see a graph of energies of the studied chemical on the computer, and use the peaks to determine what isotope is in the sample, and for instance learn whether or not your food is contaminated by radioactive chemicals. Also, there are cheaper and simpler domestic dosimeter models available to common people. For instance, here is my good old radioscan dosimeter, which uses a Mica sensor for detecting any kinds of radiation. Also, there exist cheaper dosimeters with Geiger-Müller counters, but they are not as precise. But still, it's better to have such one than not to have any. There are new dosimeters for more advanced users, which can even show the gamma spectrum of the studied isotope. But still, it takes a rather powerful radiation source to get the spectrum. A lead case is required to detect low radiation level contaminations. Yes, things are fairly simple when it comes to controlled sources and localized contaminations. A single device is required for measuring them, because it's not that difficult to measure a single radioactive object. But, for instance, in order to detect radioactive contamination on a large territory, after for example a nuclear accident, more expensive and specialized equipment is needed. A huge and highly sensitive detector with 2 huge sodium iodide crystals is used for such purposes. It costs over 100,000 euros. Usually it is installed in vehicles, and it studies the environment with the aim of detecting radioactive contamination. Because it has large scintillation crystals, such a detector can spot an increase in the radiation level from a long distance, and it can do that very quickly. For instance, such detectors were used after the nuclear accident at the Fukushima nuclear plant, where helicopters were used to create a map of the radioactive contamination in order to determine what areas were the most dangerous. With the help of such detector, you can create an entire map of different levels of radiation, and after that, you can forward these data to the liquidators. But still, for instance, in spite of all measurements and precautions, when a large-scale nuclear accident happens, both in the air as well as on the ground, there can be a mix of many different isotopes, emitting both gamma, alpha and beta radiation, and you can completely shield yourself only if you carry a huge concrete wall with you or a piece of lead weighing half a ton. That is why the only possibility to avoid exposure to serious radioactive contamination is evacuation or hiding underground, especially during the first 2 or 3 days after the accident, until the most dangerous and short-lived radioactive isotopes decay. After that you can go out, but still it's best to wear a mask and tight-fitting clothes in order to protect your lungs from radioactive dust and other parts of your body from radioactive particles. But in reality, it's not necessary for common people living far from nuclear plants to wear masks when going out, because they will make little difference with you being so far from the epicenter. You can learn about a possible nuclear accident using the options mentioned earlier, which include filtration stations and constant monitoring. Of course, if you happen to be right in the epicenter of a nuclear accident, you need to put on a mask to protect your airways from radioactive dust. All that will be left to do after that is to get as far from the radiation as possible. That's why it's always best to have a dosimeter rather than not have it. Squarespace is an online platform for creating your own website with huge e-commerce functionality. Manage your inventory, do your blog keeping, and promote your products with Squarespace. And engage with your audience with built-in feedback, replies, likes, and categorization of posts. And exclusive content for community members will help you generate even more revenue. Go to squares.com at the link in the description. Check out the free version. And once you have tested it, click on squarespace.com/toysoy2 and save 10% on the first website or domain purchase. So, I think after watching this video, you'll know more about radiation and how to measure it, and how to behave after, for example, a nuclear accident. And if you like this video, don't forget to give it a thumbs up and subscribe to my channel to see many more new and interesting.